Hi friends, how are you? I hope everyone is fine and safe. Myself, I am A.D. Chandrasekharan. This video lecture on Cauchy's residue theorem and its applications. First of all, this Cauchy's residue theorem is derived from Cauchy's fundamental theorem, particularly for multiply closed curves. Now let us see the statement of the theorem. The statement says that if the function f of z is analytic at all points inside and on a simple closed curve C, except for a finite number of isolated singularities, namely z1, z2, etc., zn inside C, then integral over C f of z dz is equals to 2 pi I into sum of the residues of f of z at each of its poles. Once again, I repeat the statement. If f of z is analytic inside and on a simple closed curve C, except a finite number of poles z1, z2, etc., zn inside C, then integral over C f of z dz is nothing but 2 pi I into sum of the residues z equal to z1, z equal to z2, etc., z equal to zn. Let us see how to get those residue values. So this second slide, it clearly shows you that the formula for the evaluation of residues. The first formula is particularly f of z at a simple pole z equal to e. Simple pole means order is 1. Then the residual of f of z at z equal to a is equal to limit z tends to a, z minus a into f of z. The second formula is the generalization of the residual values. So the second one is f of z at a pole z equal to a of order n. So order is n. So the residue of f of z at z equal to a of order n is equal to limit z tends to a 1 by n minus 1 factorial. Let us differentiate d by dz of n minus 1 term to the term z minus a full power n into f of z. So the order is n means we differentiate n minus 1 time to the term z minus a full power n into f of z. Behind this, we multiply 1 by n minus 1 factorial. Suppose if I substitute n equal to 1, which gives the first formula. If n equal to 1, what happened? 1 minus 1 is 0 factorial is 1, so 1 by 1 is 1. So the power is also 0, so no differentiation. So n equal to 1, so z minus a into f of z, that is the first formula. And third one is one special case. A residue of f of z, but f of z is p of z by q of z model at a simple pole z equal to a, then the value is limit z tends to a p of z by d by dz of q of z. So what's the mean that? That means that differentiate the denominator alone with respect to z, then apply the limit. The fourth and last model, suppose the residue of f of z at a simple pole z equal to a. In other way, we can expand the given f of z as a Laurent series expansion. In that Laurent series expansion, the coefficient of 1 by z is the required residue of f of z at z equal to a. Coefficient of 1 by z in the Laurent series expansion of f of z at the pole z equal to e. So these are the four different types of formula. Let us see the problems under each category. So I just give the list of problems here. First one. So let us see the heading. The problems in Cauchy's residue theorem. Evaluate the following integrals using Cauchy's residue theorem. The first one is integral over c cos phi z squared plus sin phi z squared by z minus 1 into z minus 2 dz, where c is mod z equal to 3. Second one is integral over c z minus 1 by z plus 1 whole squared into z plus 2 dz, where c is mod z minus I equal to 2. Third one is something interesting. Integral over c tan z dz, where c is mod z equal to 2. The fourth one is integral over c z squared e to the power 1 by z dz, where c is mod z equal to 1. So let us move on to the first problem. The first one is integral over c cos phi z squared plus sin phi z squared by z minus 1 into z minus 2. So I can consider the whole thing is f of z. Now this looks like integral over c f of z dz model. So I want to apply the Cauchy's residue theorem, isn't it? Now we find out first the poles. It is clear that the poles of f of z are nothing but the denominator equal to 0. So by that way we will get z equal to 1 and z equal to 2 are the two poles of order 1. That is simple pole. But what is the given circle for the first question? Mod z equal to 3. That means the circle whose radius is the origin 0 and origin is the center and the radius is 3. C is the circle whose center is the origin and the radius is 3. So cannot exceed the radius value. Got it? So let us substitute the first pole z equal to 1 in the C in the place of z. We get modulus of 1 is 1. It is obvious that it is less than 3. So it lies inside the given circle. And in the similar way, let us substitute z equal to 2 in the C. Modulus of 2 is 2. Yeah, 2 is also less than 3. That means that both the poles are lies inside the given circle. Got it? So both are lying inside. Let us find the residue of f of z at each of the poles. That is z equal to 1 and z equal to 2. What is the order? The order is 1. So simple pole. Let us use the formula. The first formula is, as we know that the residue of f of z at z equal to a, that is simple pole, is nothing but limit z tends to a, z minus a into f of z. Here the a is 1 in the first case. Got it? Substitute a equal to 1, we get z minus 1 into f of z. So f of z is given. The corresponding pole term get cancelled, z minus 1 is z minus 1. So the balance is cos phi z squared plus sin phi z squared by z minus 2. Now substitute z equal to 1 in the place of z. We get cos phi plus sin phi by 1 minus 2. Cos phi is minus 1, sin phi is 0. So denominator is also minus 1. So the final answer is 1. So this is the residue of f of z at the pole z equal to 1. In the similar manner, let us find out the residue of f of z at z is equal to 2. What is the order? Order is also 1 only. That is simple pole. So the formula is the same. Substitute a equal to 2 here into f of z. So the corresponding pole term get cancelled, z minus 2, z minus 2. So in the rest of the term, use z equal to 2, we get it is cos phi 2z squared plus sin phi 2 squared. So that means cos 4 pi plus sin 4 pi in the numerator. Denominator is 2 minus 1 is 1. Sin 4 pi is 0, cos 4 pi is plus 1, so 1 by 1 is 1. So I found both the residue value. Now let us apply the Cauchy's residue theorem. By Cauchy's residue theorem, integral over c f of z dz is equal to 2 pi I into sum of the residues of f of z at each of its pole. That means 2 pi I into residue of f of z at the pole z equal to 1 plus a residue of f of z at the pole z equal to 2. Let us substitute the residual value, that is 1 plus 1, 2. 2 into 2 pi I is 4 pi I. You understand? This is the first one, a simple question. Let us move on to the second sum. The second problem is evaluate integral over c z minus 1 by z plus 1 whole square into z plus 2 dz. So this time I took the whole thing is f of z, that is z minus 1 by z plus 1 whole square into z plus 2. Now it is observed that the poles of f of z are the denominator function equal to 0. So by that we will get z equal to minus 1 of order 2. It is also known as double pole. Order 2 means double pole. And z equal to minus 2 is order 1 or simple pole. Let us check out whether these poles are lies inside or outside or on the given circle mod z minus I equal to 2. So what is this? 2 is the radius. Got it? Let us substitute z is equal to minus 1 in C. So I found that mod minus 1 minus I. What is the modulus of a complex variable? Sum of the squares of the real and imaginary parts under the square root. So the same idea, square root of minus 1 whole squared plus minus 1 whole squared is square root of 2 is 1.414. So it is strictly less than 2. So it is lies inside. At the same time, substitute z equal to minus 2 in the given C. Mod z minus I is equal to 2. In the place of z equal to minus 2, I found that the answer is root of minus 2 whole squared plus minus 1 whole squared is nothing but root of 5. Root of 5 value is approximately 2.236. So it is greater than the 2. That means that this point is lies outside. This pole is lies outside. Once the pole is lies outside the given circle, immediately we say the residue of f of z at the outside pole is 0. Got it? So among the two pole, one is lies outside, so it is we immediately get the answer 0. What about the inside one? The z equal to minus 1. Let us find out the residue of f of z at z equal to minus 1. But here the order is 2, double pole. So what is the formula for the order n? So this is the formula for order n. Limit z tends to a 1 by n minus 1 factorial d by dz of n minus 1 into z minus a full power n f of z. Here a equal to minus 1 and the order n equal to 2. Let us substitute here. We get limit z tends to minus 1, 1 by 2 minus 1 factorial d by dz of 2 minus 1 z minus of minus 1 whole squared into f of z. That means that 1 by 1 factorial is 1. We differentiate only one time because order is 2. Got it? Z plus 1 whole square term get cancelled. The remaining is z minus 1 by z plus 2. Let us differentiate this by using the division rule, that is u by v formula. V squared v u dash minus u v dash. So we found that z get cancelled. So 2 minus of minus plus 1, that is 3 in the numerator divided by z plus 2 whole square. Substitute z equal to minus 1, we get minus 1 plus 2 is plus 1. 1 square is 1, 3 by 1 is 3. So I found the residue of f of z at z equal to minus 1. Now by using the Cauchy residue theorem, it is integral over c f of z dz is equal to 2 pi I into sum of the residues. Understand? Here the poles are minus 1 and minus, that is plus 2. I think it is plus 2. For the plus 2 it is 0. It is minus 2 only. Yes, minus 2 it is 0 because it is lies outside. And z equal to minus 1, we found that its answer is 3. So 3 plus 0, 3 into 2 pi I is 6 pi I. So this is the second one. The third sum is integral over c tan z dz. So what is my f of z? Tan z. So we cannot do like a previous type. Here c is mod z equal to 2, that is the radius is maximum 2 only. So let us rewrite the given f of z is equal to tan z as sin z by cos z. So it is named as p of z is the numerator, q of z is the denominator. That is sin z is numerator, p of z, q of z is cos z. It is found that the poles of f of z are given by the cos z equal to 0. When we get cos value 0, plus or minus pi by 2, plus or minus 3 pi by 2, plus or minus 5 pi by 2, etc. etc. So that means generally plus or minus 2n plus 1 pi by 2. For n equal to 0, 1, 2, 3, etc. of order 1. That is simple pole. But the given circle is mod z equal to 2. So let us consider n equal to 0. We get z equal to plus or minus pi by 2. Pi by 2 value is approximately 1.54. Let us substitute z equal to plus or minus pi by 2 in the C. That is modulus plus or minus pi by 2 is equal to 1.57. It is strictly less than 2. Got it? Now what about when n equal to 1? Suppose in z, if I substitute n equal to 1, we get plus or minus 2 plus 1, 3 pi by 2. How much 3 pi by 2? It is 4.712. So by substituting z equal to plus or minus 3 pi by 2 in the given circle, this gives 4.712. That means that it is greater than the 2, the radius value. It is obviously lies outside. So similarly, let us go for n equal to 2, just plus or minus 5 pi by 2, n equal to 3, we get 7 pi by 2. All the poles are lies outside except the plus or minus pi by 2. So this is the only simple poles are lies inside the given circle mod z equal to 2. Let us find out the residue of f of z at plus pi by 2 and minus pi by 2. Got it? But this time the f of z is looks like p of z by q of z model. That means we apply the formula residue of f of z at z is equal to a is equal to limit z tends to a p of z by q dash of z. That means differentiate the denominator alone. So what's the p of z? Sin z. What's the denominator? Cos z. So differentiate cos z with respect to z, we get minus sin z. After cancelling the sin z, we get minus 1. So there is no z at all. So no need to apply the limit actually. So the answer is minus 1. At the pole z equal to plus pi by 2. In the same manner, at z equal to minus pi by 2, again is sin z term get cancelled, minus 1. No need to apply because there is no z term at all, so no need to apply the limit value. So minus 1 for the residue of f of z at the pole plus pi by 2 as well as the minus pi by 2. So by using Cauchy's residue theorem, 2 pi I into the residue of f of z at z equal to plus pi by 2 plus residue of f of z at z equal to minus pi by 2. That means minus 1, minus 1, minus 2. Minus 2 into 2 pi I is minus 4 pi I. Okay. Let us move on to the last model, the fourth model. Integral over c z squared e to the power 1 by z dz, where c is mod z equal to 1. It's a unit circle, center is the origin, radius is 1. So let us consider z squared into e to the power 1 by z as my f of z. It is very clear that z equal to 0 is the only pole which lies inside mod z equal to 1, isn't it? As we know that the residue of f of z at z equal to a is the coefficient of 1 by z in the Laurent series expansion of f of z. So we are going to apply the Laurent series expansion. We cannot apply the limit z tends to 0 because when I apply limit z tends to 0, this obviously 0 only. Got it? Let us see. Let us expand the z squared to the power 1 by z. How to expand z squared to the power 1 by z? Yeah, z squared is fixed here. I would like to use the exponential series. In the place of z is 1 by z. So 1 plus 1 by z by 1 factorial plus 1 by z whole square by 2 factorial plus 1 by z full power 3 by 3 factorial plus etc. up to infinity. That means that 1 plus 1 by 1 factorial is z in the denominator, is z square in the denominator, is z cube in the denominator. Let's multiply z square into the terms. We get z square into 1 is z squared, z square into 1 by z is z, and z square get cancelled. It is 1 by 2 factorial is 2, and here 1 z square is get cancelled. So 1 by 3 factorial into z. This 3 factorial is 6. So the coefficient of 1 by z in this expansion of f of z is 1 by 6. So this is my residue of f of z at the pole z equal to 0, right? So 1 by 6 is the residue value. So this is the very special type to get the residue with the help of the Laurent series expansion. Do you remember that? What is the name of 1 by z? This is known as the principal part, because based on the principal part only we can classify the singular points into the three types. What are they? If there are no terms in the principal part, it is called the removable singularity. There are finite number of poles, that is finite number of terms in the principal part, it is called the pole. And there are infinite number of pole terms, it is called the essential. So now the residue of f of z is the way, another way to get the residue of f of z with the help of Laurent series expansion is the coefficient of 1 by z. Here it is 1 by 6. Got it? Now by using the Cauchy's residue theorem, we obtain that it's 2 pi I into residue of f of z at z equal to 0. That is 1 by 6. So we got the answer finally, pi I by 3. I hope you understand all the 4 different types. Okay, let us try yourself your few problems by using Cauchy's residue theorem. Integral over c dz by sine z, where c is mod z equal to 4, the answer is minus 2 pi I. When we get sine z equal to 0, 0 plus or minus n pi, isn't it? That is plus or minus pi, plus or minus 2 pi, etc, etc, but 4 is the radius. So let us collect all the poles within the circle, then use the residue theorem. Second one, integral over c is e to the power z by z minus 1 into z plus 2, where c is mod z minus 1 is less than 1, not equal to, less than 1. What are the poles? 1 and minus 2, right? If I substitute 1 here, 1 minus 1 is 0, so 0 less than 1, it lies inside. When I substitute minus 2, what happened? Minus 2 minus 1 is mod minus 3 is plus 3. Plus 3 means it is lies outside, so it is 0. Okay, so answer was given for your verification. Please work out the problem, then check the answer. 2 pi I by 3, that's the correct answer. Third one, the similar type, answer is given minus 5 pi I by 4. Let us see, these types of problems we can do by using Cauchy's integral formula, but there we have to first factorize this with the help of method of partial fraction. But here there is no such confusion. Directly we can consider as f of z the whole function. So apply the residue theorem. So I feel and I also strongly recommend all of you, suppose the question is simply evaluate, the best and easiest way is use residue theorem. Okay, so the last one, z minus 3 by z square plus 2z plus 5, so when I factorize this by using the quadratic formula, the roots are probably minus 1 plus or minus 2i. Okay, so the roots are complex as well, the poles are complex. There are 3 regions given. One is mod z equal to 1. For this mod z equal to 1, the answer is 0. The second circle is mod z plus 1 minus I equal to 2. For this, the answer is pi into I minus 2 or 2 minus 2 plus I. Third circle is mod z plus 1 plus I is equal to 2. For this circle, the answer is pi into 2 plus I. So the circle only decide the final answer, depends upon the circle. Okay, this video lecture is really helps you to get some ideas about the Cauchy's residue theorem and its applications. Thank you. Thank you so much for listening and watching this video lecture patiently. Thank you. Take care. Bye.